which these channels open or close. For example, there is a site for the binding of steroids, for the binding of barbiturate drugs. Many of our pills that we take at bedtime that can modify the way people fall asleep are acting at a site deep within this receptor complex here. There are sites on the extracellular side that likewise can modulate the flux of current through these channels. Again, drugs that are useful pharmacologically and are important drugs in the medical armamentarium. And a variety of other binding sites for drugs that are not illustrated here, including alcohol. Now, this particular ionotropic receptor allows for the passage of chloride ions. So chloride ions pass through a selectivity filter here, which are favorable for this monovalent anion to pass down its concentration gradient. As illustrated here, that concentration gradient is from inside the cell to outside the cell, which is typical of an immature neuron, as we'll talk about in a little while. Now, let's talk about the currents that pass through ligand-gated ion channels. And in order to understand the principles involved, we need to revisit Ohm's law. So you will recall that we talked about Ohm's law as being V equals IR, and we were able to rearrange that in terms of current and indicated that current equals the inverse of resistance, which is a conductance term, times V. And that V term we could expand in terms of the driving force for a permeant ion as the difference between the membrane potential and the reversal potential for the permeant ion. So we can apply the very same principles to the movement of ions through a ligand-gated ion channel. What's different here is that the channel is gated not by voltage, but by the binding of a neurotransmitter to its receptor. So when we do that, what we see is that the current, which here is called PSC for postsynaptic current, is equal to the ligand-gated conductance, the G term, times the driving force. Now, if the conductance of this channel happens to be greater than 0, this is what would happen when a neurotransmitter binds, then we would expect there to be current provided that we have a driving force. If there's no driving force, that is, if the membrane potential is precisely the reversal potential for the active conductance, then even though we may have a significant value of conductance, then there will be no postsynaptic current if the driving force term equals 0. Okay, now I want us to consider how this version of Ohm's law applies to understanding the conductance of the nicotinic acetylcholine receptor that we have at our end plates on our muscle fibers. So let's turn our attention to the neuromuscular junction. So this is the place where our alpha motor neurons synapse upon our skeletal muscle fiber, as illustrated over to the right. And what we see here is an axon that makes contact with a muscle fiber. And we can experiment upon this preparation. Now, I'd like to take you through some data that are derived from such experiments. So notice that we can stimulate the axon with a microelectrode. We can voltage clamp the muscle fiber with a voltage clamp amplifier. So we can measure the membrane potential. We can pass current to establish whatever membrane potential is of interest to the experimenter. And so what we're looking at here is a recording of end plate current. So this is a kind of a postsynaptic current recorded from a muscle fiber. And notice that the muscle fiber is voltage clamped at different levels, from a rather hyperpolarized potential of 110 millivolts all the way up through an extreme depolarized potential of plus 70 millivolts. And when we first look at the extreme hyperpolarization, what we find is that there is a significant inward current. So again, negative current here by convention is an inward current carried by a cation. So with 110 millivolts of hyperpolarization. Stimulating this axon leads to a strong inward current. If we cut that hyperpolarization in roughly half and now set the membrane potential to minus 60 millivolts, we have about half as much inward current flowing into that muscle fiber. Now notice what happens when we voltage clamp to 0 millivolts. We see essentially no current at all in this muscle fiber when we stimulate the axon. So keep that in mind. And finally, if we are to depolarize the muscle fiber to plus 70 millivolts and then stimulate the axon, what we see is not an inward current at all, but an outward current. So this behavior should look somewhat familiar to you because we saw similar behavior when we considered the impact of membrane potential on the currents that pass through voltage-gated ion channels. Only here, the ion channel is gated not by voltage, but by the binding of acetylcholine to its receptor. So note, for example, that we have inward currents at hyperpolarized potential, outward currents at depolarized potential, and no net current at 0 millivolts. So that should perhaps give you some insight as to what might be the currents that are flowing through this ion channel. Now, in order to help you think through that, I want you to be able to relate our version of Ohm's law that we're revisiting here in the context of looking at end-plate currents at the neuromuscular junction. And I want you to think about the following set of study questions that you're about to see, and they're also prepared for you at the end of the tutorial notes. So why don't you take a few minutes now and pause the recording and consider the following set of study questions.